Proof by induction, part 6. Proof by induction that the sum of r times, that dot means times, r factorial equals n plus 1 factorial minus 1, where r starts from 1 all the way to n. So what we're doing is we need to define, first of all, we need to define the word factorial. So this exclamation mark here is factorial. Best way to explain this is give an example. So factorial of 4 factorial will be equal to 4 times 3 times 2 times 1, and that equals to 24. 4 times 3 is 12. 12 times 2, 24. 24 times 1 is 24. What about 3 factorial? 3 factorial will be equal to 3 times 2 times 1. And that's equal to 6. 2 factorial will be equal to, you do 2 times 1, and that equals to 2. 1 factorial is equal to 1, and 0 factorial is equal to 1. So that's what factorial means. Now that we know what factorial is, we can do the proof by induction. In this case, we want to show that the left-hand side is equal to the right-hand side. So that will be the first operation, is to show that the statement is true for n equals 1. And we say when n equals 1, we would have 1 times 1 factorial will be equal to 1 plus 1 factorial minus 1. So in this case, we have the left-hand side and the right-hand side to look at. And for the left-hand side, we would have 1 times, because the period here, it means times 1 factorial, and that will be equal to 1 factorial is 1 times 1, that's just equal to 1. On the right hand side, we would have the 1 plus 1 factorial minus 1. 1 plus 1 is 2, that's 2 factorial minus 1. We know 2 factorial is 2, that's 2 times 1. So that'll be 2 minus 1, and that equals 1. So now we've proved that the right hand side is equal to the left hand side, and that is true for that statement. So we have shown that the statement is true for n equals 1. For operation 2, we have to assume that the statement is true for n equals k. And for that to happen, we would have to, so if we write the equation again, and this is the equation, we're going to transform the n into k, and that is n equals k. So we've got to replace the n with the k, and likewise here as well, n becomes k. And this is going to be used in the next operation, operation 3. We need to prove the statement is true for n equals k plus 1. So here's the equation, and we're going to replace the n with k plus 1. And the expected result will be, the n here is now k plus 1 plus 1, that will be k plus 2 factorial minus 1. So this is the end game. That's what we want. Let's simplify it. K plus 2 factorial minus 1. So we want to show that n, when n equals k plus 1, we'll get that. But we're not going to use this. We're going to use step 2 to get that, which means we can now write the equation again with step 2 from r, starting with 1 all the way to k, plus the last term, and the last term is k plus 1. And so we have to replace that with k plus 1 and that with k plus 1 for the last term. K plus 1 times k plus 1 factorial. This is for the last term. So k all the way to k plus k plus 1 the last term. So we just replace that with k plus 1, k plus 1. Now we're going to simplify these, and once simplified, we should get that. So we replace that with the step 2, which is what we got when we replace that with k in step 2. And then we add the last term to it. Now we need to take a common factor out, which is k plus 1 factorial. There's k plus 1 factorial here, k plus 1 factorial here, and this one is just the last term, last number here. So we can rearrange this to make it easier. K plus 1 factorial plus k plus 1 times k plus 1 factorial, then minus 1. So to make it easier to see, so we're going to take a common factor here between these two terms. So that's k plus 1 factorial, so that would be 1, plus what's left, k plus 1, then minus 1. That's the minus 1 here. Now we can now simplify it. Get k plus 1 factorial, and this will be times k plus 2, then minus 1. So the problem is this one here. So what is k plus 1 factorial times k plus 2? We know what that is. What is k plus 2 factorial? Well, k plus 2 factorial will be k plus 2 times k plus 1, right? Times k, because you're decreasing by 1 every time whenever you do your factorial. That would be times k minus 1, and then all the way to 1, which means you can see that k plus 2 here, and now you see k plus 1 factorial. Well, k plus 1 factorial is k plus 1 times k minus 1. So that is k plus 1 factorial, and that's k plus 2. So that means k plus 2 factorial is this. Give another example. If you have 7 factorial, let's say that's k plus 2. So that would be 7, right? Because k plus 2 is 7 factorial. So that would be 7 times 6 times 5 times 4. What about 6 factorial? This is 6 factorial. This is 5 factorial. This is 4 factorial. So that means 7 factorial means what we got here. Well, we got 6 factorial here times 7. So that makes that 7 factorial. Because I've got 6 factorial here, then times 7. You remember k plus 2 is 7. So now that's 7 factorial. So therefore I can rewrite this as k plus 2 factorial minus 1, which is what I wanted. Because I've replaced that with k plus 1. So k plus 1, we make it k plus 2 factorial minus 1, which is that. And I've derived it using the second operation. That's correct, and that's correct, and that's been proved. Finally, we need to do operation 4, where we must write the 4-point statements to get the full mark. The first one being, since the statement is true for n equals 1, we must write that down, followed by, and if the statement is true for n equals k, we must write it down, followed by, then it is true for n equals k plus 1, followed by, the statement must be true for all n greater than 1 or equal to 1. All of these 4 statements must be written down to get the full mark.